You're listening to DTFHN for April 3rd, 2026. I'm your warranty-voided host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where everyone knows how to build it better, but nobody's shipping. Today reeks of bold promises and quiet contradictions. Let's go find out who meant it. A website called onlyu.eu, promising European alternatives to every US app you use, is hosted on Cloudflare, an American company, subject to the Cloud Act, the very law the site warns you about in bold text on its homepage. You cannot make this up. The site's pitch is simple. GDPR is stronger than American privacy law, so swap your US tools for European ones. Google for Ecosia, Dropbox for Tresorit, Slack for Rocket.chat, 120 alternatives, neatly categorized. And look, the impulse is sound. Data sovereignty matters. Where your bits live, and which government can subpoena them. That's a real concern. Not a theoretical one. The Cloud Act genuinely does allow U.S. authorities to compel data handover regardless of server location. That's not fear-mongering. That's statute. But the execution here is a comedy of errors, and the Hacker News comments are doing the autopsy in real time. Someone ran the DNS, Cloudflare. Someone else noticed the site is mostly affiliate links, quietly steering you toward services that pay referral fees while skipping better alternatives that don't. The homepage declares Europe does it better in letters big enough to read from orbit. And meanwhile, Proton, the poster child for European privacy, just got caught building their new video conferencing tool on infrastructure subject to the exact jurisdiction they market against. The deeper problem isn't hypocrisy, though. It's that European isn't a technical specification. It's a flag you wave. The commenter who asked what European even means here hit the real nerve. Is it headquarters? Server location? Company registration? Ownership? Because in a world of multinational cloud providers and nested infrastructure dependencies, geography is the wrong abstraction for trust. You know what is the right abstraction? Source code. If you can read it, audit it, fork it, and host it yourself, then it doesn't matter if the developer lives in Berlin or Bangalore or Buenos Aires. Self-hosted open-source tools solve the data sovereignty question at the root. Nextcloud instead of Dropbox. Not because Nextcloud is European, but because you control the server. Jitsi instead of Zoom. Not because of jurisdiction, but because the code is yours to inspect. The irony is that several tools on this list actually are open source, but the site buries that as a feature because it's selling geography when it should be selling architecture. Swap your apps because you can see inside them, not because of which passport the CEO holds. The tools exist. Some of them are even on this list. Just maybe don't trust the list itself to tell you which ones matter. This one made me genuinely happy when it crossed the feed. Every Mac with Apple Silicon now ships a language model. It's baked into the operating system starting with macOS Tahoe. Runs on the Neural Engine and GPIO. No cloud calls, no API keys, no account. The model is just sitting there on your disk, waiting. But Apple, being Apple, locked it behind Siri and writing tools. There's no terminal command, no HTTP endpoint, no way to pipe text through it. You've got a language model on your machine and no way to talk to it unless you write a Swift app from scratch. A developer looked at that and said, I'll fix it in one binary. Apfel is a Swift, a 6-line core that wraps Apple's foundation models framework and cracks it open 3 ways. First, as a straight Unix command line tool. Then, Stout, pipe it into whatever you want. Second, as an OpenAI-compatible HTTP server built on Hummingbird, which means any tool that speaks the OpenAI format can now talk to the model already on your Mac. Third, as an interactive chat with context management. Let's pull this thread on the architecture, because it matters. Apple built a capable on-device inference stack, neural engine scheduling, memory-mapped model weights, tight integration with the unified memory architecture on Apple Silicon. The engineering is genuinely impressive. They shipped a model that runs locally with zero setup, which is exactly what you want for privacy, for latency, for offline use. Then, they welded the door shut and said the only way in is through Siri. Apfel doesn't modify anything. It doesn't jailbreak the model or bypass security. It just calls the same Swift API that Apple's own apps use and exposes it through interfaces that actual developers can compose with. A Unix pipe, an HTTP server, the two most universal integration points in computing. One of the Hacker News comments asks whether you could use this as a sub-agent for a more capable model like Claude. That's the right instinct. A fast, free, local model handling simple classification, summarization, or routing while a frontier model handles the heavy reasoning. That's a genuinely useful architecture, and it costs nothing because the compute is already in your laptop. Apple did the hard work. They trained the model, optimized the runtime, shipped it to millions of machines. Then they forgot to include a door. Apfel is just a door. But doors are how you get from a product to a platform, from a feature someone else controls to a tool you can build on. And now the door is open. Moving on. The top comments on this one are fighting about Ollama versus Llama.cpp versus LM Studio versus Unsloth Studio. And honestly, it reminds me of something from woodworking. There's this eternal debate among woodworkers about whether you should use hand tools or power tools. The hand tool purist will tell you a Japanese pull saw gives you more control. The power tool folks say a table saw is faster. And meanwhile, the person who actually built the cabinet is already sitting in the next room enjoying dinner. This just is a cabinet. It's a straightforward copy-paste recipe for getting a 26 billion parameter language model running on a Mac Mini with persistent memory loading and an OpenAI-compatible API endpoint. Brew install, pull model, configure a launch agent, done. Someone on Hacker News complains that Ollama is overly stripped down compared to alternatives. That's the point. That's the entire point. Let's talk about what's actually happening under the hood here, because the engineering deserves attention. Gemma 426b is a mixture of experts model that only activates 4 billion parameters per token. Google trained a model that learned which parts of itself to wake up for each task. The commenters correctly note this is doing the absolute minimum work while still delivering quality output. In biology, this is how neurons fire. Your brain doesn't light up every region to process a sentence. It routes selectively. Sparse activation. Google built a model that thinks the way brains think, and it fits in 17 gigabytes. Now pair that with Ollama's MLX backend on Apple Silicon. No configuration. The framework talks directly to the unified memory architecture. GPU and CPU sharing the same pool. That launch agent trick in the gist. Sending an empty prompt every 5 minutes to keep the model warm is a hack. A beautiful, pragmatic hack. Set Ollama comp a live to -1, and the model just lives in memory permanently. Your Mac Mini becomes an always-on inference server with an API at localhost 11434. Pull this thread further. That API is OpenAI compatible. Every tool, every agent framework, every coding assistant that speaks the OpenAI protocol can now point at your desk instead of a data center. The compute is already paid for. The electricity is already flowing. The model weights are open. Google released them, Ollama packaged them. Apple's silicon runs them, and a person on the internet wrote the recipe that ties it all together. 4 commands to install, $0 per query. Forever. This is builder culture at its finest. Not the person who designed the fanciest saw, but the one who wrote down exactly how they built the cabinet so you could build one too. Moving on. 26 billion parameters, 4 billion active. That ratio, buried in the model name, is the detail worth pausing on. Gemma 4's largest variant carries the full weight of a 26 billion parameter model, but only fires 4 billion parameters per token. The rest sit idle, waiting for the right query to wake them up. Sparse mixture of experts. It means the knowledge of a model 5 times its active size runs on hardware that has no business being this capable. Someone in the Hacker News comments tested it by generating pelicans. The 2 billion and 4 billion parameter models produced, quote, unrecognizable pelicans. The 26 billion, BA4 billion parameter models produced, quote, unrecognizable pelicans. The 26 billion BA4 billion model produced what they called the best pelican they'd seen from any model that runs on a laptop. A laptop. Not a rack, not a cloud instance billed by the minute. A machine you carry in a bag. And this model doesn't just generate images. It reasons. It calls functions. It navigates applications. Google's own description uses the phrase autonomous agents that plan and complete tasks on your behalf. This is the architecture for software that acts, not software that answers. Which raises the question nobody in the comments is asking directly. Why is Google releasing this as open weights? This is a company that built its empire on proprietary search ranking. Proprietary ad targeting, proprietary everything. And here they are, publishing model weights that let anyone build autonomous agents on consumer hardware. Within hours of release, Unsloth had quantized versions on Hugging Face. Modular had optimized inference running on the latest NVIDIA and AMD chip. A member of the Gemma team showed up in the comments to answer questions. This is not the behavior of a company protecting a moat. This is the behavior of a company that decided the moat is somewhere else. The cynical read is that Google wants the ecosystem dependent on its architecture. The generous read is that open models are simply better strategy when your real product is the infrastructure people run them on. Either way, the outcome is the same. The weights are public. The quantizations exist. The community is already building. Whatever Google's internal calculus, a 26 billion parameter agent model now runs on a laptop, and no one can take that back. 5 stories in, and we haven't even gotten to the hardware yet. Let's fix that. The strongest argument against caring about this chip goes something like this. Espressif is a small company competing against NXP, ST Microelectronics, Qualcomm Texas Instruments. Companies with decades of silicon design experience, massive fabrication partnerships, and enterprise sales channels that stretch into every factory and data center on Earth. A dual-core RISC-V microcontroller running at 320 megahertz is cute, but it is not competing with the ARM ecosystem. It is not competing with the billions of Cortex-M chips already deployed. The professional embedded world runs on proven architectures with proven tool chains and no spec sheet changes that. Now, let me dismantle that. Strip this down to first principles. What does an EOT device actually need? It needs to connect to a network. It needs to process sensor data or run a display. It needs to do this cheaply, securely, and with low power. That is the actual requirements list. Everything else is ecosystem, lock-in, dressed up as engineering necessity. The ESP32S30WA puts Wi-Fi 6, Bluetooth 5.4 with LE audio, Thread, Zigbee, and Gigabit Ethernet on a single die, a RISC-V die. Not ARM, not licensed, not subject to a corporation in Cambridge deciding next year's royalty structure. The instruction set is open. The development framework, ESP-IDF, is open source. The Matter protocol support means these devices talk to everything without a proprietary bridge. The param bandwidth deserves attention. 250 MHz, 8-bit DDR with concurrent flash access. One commenter flagged this as buried in the noise, and they are right. That bandwidth combined with 128-bit SIMD instructions on one of the cores means this microcontroller can do real image processing, real audio work, real edge inference. On a chip that will probably cost under $10. The comments reveal healthy skepticism. People note Espress naming is confusing. The ESP32P4 still has not hit distributors after 2 years. The MMU might not be a true SV32 implementation. These are legitimate concerns about execution, but they are concerns about timeline, not direction. The direction is what matters here. A company in Shanghai is building silicon on an open instruction set, supported by open source tools, with every wireless protocol that matters, and shipping it to hobbyists and factories alike. Every ESP32 board that a teenager buys for $12 is one more device running on an architecture that no single company controls. ARM's dominance in embedded was never about technical superiority. It was about ecosystem momentum and tool chain familiarity. RISC-Zifty chips like this erode that advantage, one product cycle at a time, not by being revolutionary, by being sufficient, open, and cheap. That is how architectural shifts actually happen, not with a bang, but with 1 billion units shipped while the incumbents are still arguing about licensing terms. We've been celebrating builders so far. Now, let's hear from someone who watched the walls go up from the inside. I once spent 3 weeks debugging a memory allocation issue on a system where someone had decided to run a full database engine inside a component originally designed to handle 4 kilobytes of shared state. 4 kilobytes. The ambition was impressive. The crash dumps were more impressive. So when I read a former Azure Core engineer describing a room full of people seriously planning to port half of Windows to a chip the size of a fingernail running Linux, on a power budget that wouldn't keep a desk fan spinning, I felt that particular flavor of recognition that only comes from watching smart people talk themselves into architecturally impossible things. The article is from someone who helped build the container platform under Docker, Azure Kubernetes, and Windows Sandbox. Granted patents, kernel-level work. This isn't a disgruntled intern. This is someone who contributed to the foundations and then watched the floors get built crooked. Now, Let me play devil's advocate for a moment. Microsoft's Azure is the second largest cloud platform on Earth. It runs a significant chunk of the U.S. government's infrastructure. OpenAI, the company everyone cannot stop talking about, built on it. You could argue the complexity is justified. You could argue that porting Windows components to custom accelerator hardware is exactly the kind of ambitious engineering that separates a hyperscaler from a hosting company. You could argue that. And then you read that 122 engineers were knee-deep in what the author frames as an impossible porting effort. That the team eventually reached a point where any code refactor was considered too risky to attempt, and that Azure OpenAI was reportedly leaking other customers' prompt responses under heavy load. The ambition defense collapses pretty fast when the system is returning someone else's data to your API call. This is what happens inside closed systems at scale. The architecture calcifies. The org chart becomes the system diagram, and the people who actually understand the foundations either leave or get outvoted by planning slides full of arrows connecting boxes that have no business being connected. The comments on this one are split between people calling it a grudge piece and people saying it explains everything they have experienced as Azure customers. Both can be true simultaneously. The deepest irony is that the overlay card runs Linux. The custom silicon at the heart of Microsoft's cloud acceleration strategy boots an open-source operating system. Because when you need something small, efficient, and reliable on constrained hardware, you reach for the thing 1,000 engineers built freely. Then, you wrap it in proprietary tooling and sell it back. The foundations are open. The lock-in is the product. And when the foundations crack, the lock-in is the only thing keeping customers from walking to the platform that got the architecture right the first time. When people start questioning who controls the infrastructure they depend on, sometimes the resistance isn't technical. Pause, it's moral. What happens when you build a system so good it delivers on time and on budget, and the people who are supposed to use it simply won't? The NHS awarded Palantir £330 million in 2023 to build the Federated Data Platform, a system to correlate patient data, waiting lists, operational information across England's hospital trusts. And by the metrics that matter to procurement officers, it's working. 123 of 205 trusts are on it. Delivery ratings are high. The spreadsheets look great. Meanwhile, senior health officials and data analysts are filing formal workplace adjustments to refuse engagement with the software. Others are working as slowly as possible when forced to touch it. Some just route around it entirely, citing tools that already existed. The platform is succeeding by every measure, except the one that matters. People actually wanting to use it. Run this forward 5 years. You have a nationally deployed data platform that a meaningful fraction of NHS staff treats like radioactive waste. The staff aren't wrong to be uncomfortable. Palantir built its reputation on defense and intelligence contracts. Its leadership's political affiliations are a matter of public record. And the fundamental question: should a U.S. defense contractor with deep ties to surveillance infrastructure manage the health data of 67 million people? It's not ideological noise. It's an architecture question. Who holds the off switch? What happens when the objective function changes? What happens when the next administration decides that data is leverage? The comments nail the procurement angle. £330 million for data collation is absurd on its face. Open source health data platforms exist. OpenEHR exists. FHIR is an open standard. The NHS could have funded a decade of open development for that price and owned the result. Instead, they bought a subscription to someone else's system with a break clause they're now scrambling to understand. The deepest irony is the passive resistance itself. NHS workers are doing exactly what you'd want a healthy institution to do. Questioning who controls their tools. They're just doing it after the contract was signed, which is the comedy and the tragedy in one. The tools to build this openly were always available. The decision to hand it to Palantir was never a technical one. It was a procurement failure dressed up as innovation. Now, when someone actually builds the privacy-respecting alternative, everyone keeps asking for, it's worth looking at what they got right and what they didn't. In GPIO, Hushmail launched with a promise that would become a template. End-to-end encrypted email. Zero knowledge. Governments locked out. By 2007, a court order revealed they'd been delivering modified Java applets to targeted users that captured passphrases before encryption. The architecture had a gap. The promise didn't survive contact with legal reality. Proton just did something structurally similar, except they did it on launch day. Let me be precise about what happened here. Proton Meet's entire marketing pitch is escaping the Cloud Act. The U.S. law that lets American authorities compel data handover from U.S. companies regardless of where the servers sit. Their blog post literally says that's why they built it. Then they built it on LiveKit Cloud, a California incorporated company governed by California law with infrastructure running on Oracle Cloud in Phoenix, Amazon EC2 in Oregon, and DigitalOcean and Google data centers. Every one of those is a U.S. entity subject to the exact law Proton claims to circumvent. This isn't ambiguous. The network forensics are clean. Active connections during a live Proton Meet session hit LiveKit-owned IP blocks on Oracle infrastructure. The stun and turn servers handling WebRTC connection establishment resolved to Oracle Cloud IPs. LiveKit's own JavaScript SDK prints its file name in the browser console during calls. The content security policy headers whitelist LiveKit Cloud domains explicitly. Proton's own privacy policy discloses it, and LiveKit's privacy policy states plainly they will hand data to law enforcement when asked. The comments service the right question. LiveKit offers self-hosted enterprise options. Proton could have run their own mesh. They chose not to. That's a business decision dressed up as a privacy architecture. What makes this worth pulling apart isn't just the gap between marketing and implementation. It's that the tools to do this properly exist and are open. LiveKit itself is open source. You can run it on infrastructure you actually control, in a jurisdiction you actually choose. Proton had every option to deliver on the promise. They shipped the landing page instead. The fix here is straightforward. Self-host the SFU. Drop the Cloud Act marketing until the architecture matches. Or just be honest about what launch day actually delivered. A video call routed through the same American infrastructure as everyone else's, with better branding. Moving on. 1 million Jupyter notebooks. Someone actually read 1 million Jupyter notebooks. Not read exactly. Parsed, cataloged, mapped the exposed surface of how 1 million people actually use pandas. And what Peterson's team found underneath all 200-plus methods was 15 operators. 15 composable primitives that could express nearly everything those notebooks were doing. That's already a beautiful compression. But the article's author, building their own data frame library, kept pulling the thread. Because some of those 15 operators share a shape. Projection, rename, group by, join. They'll change the schema. They reshape what columns exist and what types they carry. Others, like selection and sort, Leave the schema untouched and only rearrange rows. That's not a coincidence. That's structure. This is where category theory enters, and I want to be precise about why it matters. Category theory isn't decoration here. It's engineering, when you can prove that your small set of primitives composes correctly. That chaining a map after a projection produces a well-typed result. You've eliminated an entire class of runtime errors by construction. The types do the work. You don't need 200 methods because you have composable pieces that snap together with guarantees. Now here's the architectural detail worth dwelling on. The formal definition of a data frame. Ordered rows, ordered columns, symmetric, transposable, with data that can become metadata in metadata that can become data. That's what makes data frames fundamentally different from SQL tables. Relational algebra can't express transpose. It can't promote a data value into a column label. Those 4 extra operators in Peterson's algebra exist because data frames treat structure as mutable. The schema itself is data you can manipulate. And the library that falls out of this analysis is open source. The algebra is published. The categorical foundations are written up for anyone to build on. 1,000 people can now implement correct data frame engines from the same proven primitives. Instead of reverse engineering pandas quirks one deprecation warning at a time. The formal structure is the gift. It turns an API memorization problem into a composability problem, and composability problems have solutions that compound. Now, from the algebra of data to the geology of another world entirely. Jupiter's moon Io has a mountain, and its shape is telling us something. I'll work with the article content already provided in the prompt. Let me write the segment. Steeple Mountain is a nickname. The real name is Des Monts, and it sits on the surface of Jupiter's moon Io. A world so volcanically violent it has been resurfacing itself for billions of years. Someone looked at a shadow in a photograph and reverse-engineered a mountain from it. The technique is called photoclinometry. You take the shape of a shadow cast on a known surface. In this case, a sphere with Io's radius, and you work backward to reconstruct the three-dimensional object that cast it. The team used global maps of Io compiled from Juno mission imagery by Gerald Eichstadt, Jason Perry, and John Rogers. Mapped that data back onto a sphere, oriented it to match the original sunlight angle, and extracted elevation profiles from the interplay of light and dark. Manual photoclinometry, they call it, adjusting a 3D model by hand until its simulated shadows match the real one. The geology underneath this is remarkable. Io's mountains don't form like Earth's. There are no tectonic plates sliding around. Instead, billions of years of volcanic deposits pile onto the crust, forcing it downward until the lithosphere buckles and entire crustal blocks thrust upward along deep faults, like a rug compressed from both sides. The engine driving all of it is tidal friction. Jupiter's gravity flexes the interior on every orbit, with Europa and Ganymede locked in a Laplace resonance that keeps Io's orbit just elliptical enough to never let the heating stop. The data is public. The maps are assembled by independent researchers. The reconstruction methods are published and reproducible. Planetary science at its best. Someone stared at a shadow long enough to find a mountain inside it, and showed their work so anyone else could do the same. This has been your daily tech feed for Hacker News for April 3rd, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voiced by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something you'd be proud to show your work on. We'll see you back here tomorrow.